is Emilio, and I work with a metro band, and under the supervision of ours on a project called Gated Silicon Nanowires for Thermoelectric Applications, which probably for most of my audience, this looks something like this, where we have something in some other language that we don't understand what it is, or some kinds of applications that we don't know of. So throughout my talk, I'm going to be trying to translate these words back into language you can all understand. So first, I want to explain what these thermoelectric applications are. Basically, what a thermoelectric is a device that converts temperature difference directly to electricity. This is a very common thermoelectric device. I actually have one that's one. When you have a difference in temperature between this top platform and the bottom platform, you can generate electricity in these cables. There's many applications of this effect. One of them is in this case of spaceships. If you have ever wondered how spaceships work, how they go on missions for 20 years far away from the sun, this is how they actually do it. They take with them these very unstable chemicals, which in the process of decaying, they radiate heat, and that heat is used by the thermoelectric power generator to power the spaceship. There's also applications being developed in the medicine field, where you see this picture is a pacemaker, makes use of the heat radiated from the body to generate power, recharge the battery. So, despite all these applications, a lot of people don't know about thermoelectrics, and the reason for that being is that the efficiency of thermoelectric application is still not high enough to impact the market and compete against other conventional methods. So there's a demand for high efficiency in thermoelectrics, but also we need to keep in mind that we need low-cost thermoelectrics in order for them to succeed in the market. So there's a lot of research going on increasing the efficiency of different materials. One of the materials that actually meets the requirement of potential high efficiency and potential low cost is silicon. So we have done research in silicon for that reason. And actually, current research has found out that silicon in the form of nanowires decreases its thermal conductivity and increases the efficiency of silicon by a factor of 100. So further the research has been done with this silicon nanowire in order to increase its power factor, which I'll talk a bit more about later, to increase the efficiency. So to increase power factor, what people have tried is doping the silicon. As you see, this power factor is described as the Seebeck coefficient squared times electroconductivity. And the electroconductivity is related to how many carriers you have in the material. So by doping silicon and putting carriers, you can increase its carrier density. However, at the same time, you decrease the mobility as the mobility decreases as you keep putting impurities into the material. So you're limited somehow, somewhere to this mobility after you put so many impurities, it will take over and electroconductivity will not decrease anymore. So we're coming up with a new approach to find a way to increase its carrier density without having to add impurities, which increases the electroconductivity. So our approach is to have a pure silicon nanowire and pretty much a conductor, which we call the gate, and an insulator between. And it serves like a parallel plate capacitor. As you apply a voltage difference between the two, you're able to induce the desired carriers that you want in your nanowire without having to add impurities. This allows us to increase this density the density carriers, which will now be a function of the voltage that we apply between these two, the gate and the nanowire, without having to decrease mobility. So now power factor becomes a function of the gate voltage, not a function of how much impurities we put in there. So this way we can understand how power factor changes as we add different amounts of carriers into this silicon nanowire. So our goal is to understand how power factor changes with different gate voltages and find the point where it peaks for optimizing the efficiency. So here's the parameters that we need to measure. It's Seebeck times electroconductivity. So my mentor has worked on fabricating a device designed specifically to measure these two parameters. We have our Seebeck coefficient with this equation. As you see, we need to have a difference in temperature along the nanowire and measure the difference in voltage to calculate the Seebeck. So we have a heat source, which will heat up the nanowire to create a temperature gradient. And we have these electrodes, which will serve as thermometers to measure the difference in temperature and also to measure the difference in voltage. For electroconductivity, we can measure the resistance of the nanowire across the length of it, and by knowing the length and the cross-sectional area of the nanowire, we can calculate the electroconductivity. This is just a four-pros resistance measurement, which basically means we run current through the outside electrodes and we measure the voltage drop in the inner electrodes. So this is how we're actually going to do it. We're starting with the nanowire, and we have the Seebeck equation, and this is the line, which will be the heater line or the heat source. As we run current through this line, this will create Joule heating proportional to the current squared times resistance. This will create the temperature gradient across the nanowire, and now these two lines will be used as thermometers, like I said before, to measure this temperature gradient. And the way we do that is that we measure the difference in resistance before and after we apply the heat source. Resistance and temperature have a linear relationship. So to make it more clear, I have this graph, which we calibrate before making our measurements. So as you see here, our room temperature, if the resistance on the line is about 166.5 ohms, and after we apply the heat source, maybe it changes, it goes up. So by knowing the difference in resistance, we can measure this difference in temperature. So going back to our diagram, we need to measure how much difference in temperature there was before and after we apply the heat source in order to measure the difference in temperature. So for that, we need accurate resistance measurements. And again, we use a 4-probes configuration. We run current through the outside probes. An AC current with very low current because we want to avoid this Joule heating trade here. So we want to use very low currents. And we measure the voltage drop at this frequency only to get rid of the noise. We do the same on the bottom line, and calculating the difference in temperature in each line, subtracting from each other, we get the difference in temperature. Finally, to measure this Seebeck voltage, we measure the difference in voltage between these two probes. Here's a picture of how it actually looks like in real life. This is a picture through a microscope. Here we have all these pads used for, these two pads are used to send current through the heater line. These pads represent these pads, like I showed on the diagram before, as thermometers. Here's the other pad, the other lines. And this picture is zooming in the region that we're interested in with the nanowires. You can see it, here's the gate, and the nanowires is underneath. To show some data that we obtained, this plot right here represents the difference in temperature as a function of how much current was sent through the heater line. And like I said before, the heat produced by the heater line is proportional to the current squared. So it makes sense that we get this quadratic shape with the difference in temperature. And it's hard to appreciate it, but if you see, we measure this Seebeck coefficient in a silicon sheet of about 25 microns long. It's about 25 microns long. So it's about 6 times less than the diameter we heard. And we're obtaining a difference in temperature of maximum 6 degrees Celsius, which is pretty amazing, I think. We have very repeatable results. here we have the measured voltage versus heater current. It's a function of the current to the heater. Again, it follows the same trend as the previous one, as it should in this equation. And finally, we plot the seedling coefficient, which is what we're interested in. And again, it's a linear relationship as it should be. And we expected about negative 200 microvolts per Kelvin. We obtained about 211.8 to 12.5, which is very precise, as you can tell. However, this measurement was done on a silicon sheet and not actually the silicon nanowires, because we're first testing the routine to make sure it works on a silicon sheet, which is much easier to measure than the nanowires. So to conclude, the CBEC routine that we have put together and developed seems to be very precise. We get very repeatable results, but we're still analyzing how accurate it is, so we can get sources from error from the probes from the lines, which add seeded voltage also. So we expect about 200 microvolts per K. We're getting 211, but it could also be 220 or 90. We don't know. So we need to analyze how accurate it is. We also need to measure this, test this routine with actual nanowires and not just the silicon sheet. So next year we're going to be working on measuring the nanowires and actually, after we get that done, analyze how power factor changes with different gate voltages. So finally, as I come to the end of my talk, I hope I have made this slide look something like this to you. And before I take any questions, I'd like to acknowledge my mentor bank, Professor Bowers, and all the useful stuff for the help.